Okay, so now we're coming up to the dot product. Okay, this is when we're trying to multiply two vectors together. Okay, now a classic example of this that we did last year, and we weren't talking about it in terms of dot product. We looked at work. We wanted the work, and what work was it was the portion of the force that was in the direction of motion. Okay, times that distance. All right. So what I'm doing, I'm basically multiplying the force by the displacement. But I don't want all the force. I only want the part of the force that goes in the direction of motion. Okay? So now, if I take a look at this, if I break this apart, okay, I've got force that goes up like this, and I've got displacement that's going along like that. And again, I don't want all the force. And just make this long. I don't want to make it be the same length. Okay? I don't want all the force. I only want the part of the force that goes along the direction of motion. And that part would be that component right there. Okay? That's the cosine of theta. Okay? The portion of the force that's in the direction of motion, that's the cosine of theta. And it's times that distance. So really what I'm doing here is I'm saying that work, remember last year we said that was force, it was the magnitude of the force, the magnitude of the displacement. So I'm just taking the scalar portions of those vectors and multiplying it by angle, the cosine of the angle theta between them. Okay? So now, we want to look at this in a more general sense. Okay? What we're doing is taking two vectors and multiplying them together. Okay? This is going to be something that I have with, when we talk about all sorts of different quantities within physics, we take a look at what's called the dot product. Okay? Now the dot product of two vectors, okay? So let's just say I have vector A and vector B. Okay, we put a dot between them, and that's what we call the dot product. Right? In putting it into this magnitude angle formulation, it's going to be the magnitude of A times the magnitude of B times the cosine of the angle between them. Okay? Next year, when you get to college, you're going to have a little bit more of a strict way of designating what the magnitude is. You put it in absolute value brackets and everything else like that. For right now, when you see it with a hat, you know that it has magnitude and direction. When you see it without the hat, okay, without the vector hat on it, you know it's just talking about the magnitude. Okay. So now, that's pretty straightforward. So really what work is, it's the dot product. We could say, you know, this is magnitude of the force, magnitude of the displacement, times cosine of the angle between them. We could say that work is equal to the dot product between the force and the displacement. Okay? So there you go. There's your first physics equation, really, for the year. Chapter 2 had some stuff with displacement, but this is like real physics. Okay? We're not going to worry about that yet, but you just see how it works. If it's in unit vector notation, this is a case where unit vectors aren't necessarily easier. They're not really harder, they're just about the same. Okay? If I have two vectors that I want to multiply together, and they're in unit vector notation, the way that I would write it is A dot B is equal to, and you got to be careful, whenever it's in unit vector notation, people always leave the i's, j's, and k's in there. Okay? Notice, this does not, work is not a vector. Okay? This is this dot product is also called the scalar product. So this is dot product, scalar product. Another way of talking about it. Another name for it. Okay? This is just going to be the x components multiplied together plus the y components multiplied together plus the z components multiplied together. Okay? Notice no I, j, k. This gives you a scalar out. All right? So now, let's just say that I have two vectors that I want to find the dot product between them. So let's just say vector A will do the unit vector notation first. 3i minus 4j plus 12k. Vector B is 18i minus 6j plus, I don't know, 4k. All right, A dot B, okay, I take the x components and I multiply them together, 18, 36, 54. I take the y components and I multiply them together. Negative 4 times negative 6 gives you positive 24. And then you add to that the k components. 12 times 4 is 48. So now A dot B, this is going to be 102, 126. Okay, yeah, 126. All right, so that's how we do it using IJK notation. Okay. The other way, all right, let's just say that I have two vectors, and it's very helpful to know the angle between them. Okay, if they give you the angle with respect to an x and y axis, or God forbid an x, your angles between x, y, z, and for each of the two vectors, and then you have to find the angle between them, that becomes a little bit more difficult. But let's just say that we have vector A is at, the magnitude of A is 60, magnitude of B, notice there's no vector line over top of it, is 25. And let's just say that the angle between A and B is equal to 40 degrees. Okay? And we want to figure out what A dot B is. Okay? Okay, and I didn't make these vectors yet because they do have direction, but I didn't give you the direction, their absolute direction, but I just gave you the angle between them. Okay, so, but they do have direction. So A dot B is going to be, okay, if I take a look over here, magnitude of A, which is 60, magnitude of B, which is 25, cosine of the angle between them, which is 40 degrees. So A dot B is equal to, actually that's 1500 cosine 40 degrees. So A dot B is equal to 1149. Okay. Again, not really worrying about units yet. That'll be definitely in the next chapter that we have to start really caring about units. All right. So now that's dot product. Now here's an interesting thing. All right. I said that it can be very hard to figure out the angle between two vectors in magnitude angle formation. It's really hard actually to figure out what to visualize what the angle is between two vectors in IJK notation as well. So let's just say that I have two vectors here. A is equal to 4i plus 6j minus k. Let's make B, all right, it's going to be minus 5i, nothing in the j, plus 10k. If there's no j, what do you assume it to be? Pause for a second. 0, very good, okay. So now, so that the y component there for b is 0. So now we want to figure out the angle between these two vectors. Just looking at it, you're like, I have no idea. Okay? Take a moment, and I want you to try to think of a way that you can figure out the angle between these two vectors. Pause for a second. Okay, so now, actually pause for a while and try to work this out. But pause. Okay, so now, here I go. I'm going to try to solve this. What I know is, I know that A dot B is equal to AX BX plus AY BY plus AZ BZ. I also, however, know that A dot B is equal to A, B, cosine of theta. So now, here's the thing. I can do this. I can find the magnitude of A. I can find the magnitude of B. All I have to do is figure out what cosine theta is. Now I can solve for cosine theta. So let's take a look. I'm going to have to introduce one other thing here too. Another vector property that I haven't done yet. A dot B, using IJK. A dot B is equal to 4 times negative 5, so it's negative 20. 6 times 0 plus 0. Negative 1 times 10, I get minus 10. So A dot B is equal to negative 30. But it's also equal to A, B, cosine. I have to figure out what the magnitude of A is. Okay. Now, we haven't done this yet. Think about how I figured out what the magnitude of a two-dimensional vector is. Okay? The magnitude of a two-dimensional vector was the square root of ax squared plus ay squared. It's just a two-dimensional Pythagorean theorem. Okay? Now, let's think about this. I don't know how well this is going to work out. I'm doing this on the fly. So now, I have a vector whose components look something like this. So now, if I want, and we'll go up to here, similar to what we had before. Trying to make a box here so we can visualize a little bit better. But now, I can figure out what this distance is pretty easily. Okay? I've got my x squared here. This distance is my x. Okay? This distance is my z. So if I want to figure out what this portion is right there, okay, that length right there is going to equal x squared plus z squared, square root. Okay, so now I know what this is. Okay, this is x, this is z. Okay, this is a right angle between the two of them. So now, this distance right here is x squared plus z squared. Square root. But now, here's the thing. I also have a right angle right here. That's a right angle. So this distance squared plus this distance squared will give me what will give me that. Okay? I know this gets a little clouded here. But now, again, This distance squared plus this distance squared gives me that. That's along the xz plane. Okay? X squared plus z squared. If I take this distance squared and add it to this distance squared, I will get that. So now what I have here, if I just kind of pull that out to the side here, I know that this distance right here okay, this was your x squared plus z squared. Square root. I have the part that goes up. And I know this angle is 90 degrees. I know that this distance is y. And this is my three-dimensional distance that I'm trying to find. Well now, this distance squared plus this distance squared gives you this. So now, all of this is what I'm trying to tell you is the three-dimensional Pythagoras is, let's just call this distance d. D squared will equal this distance squared, which is x squared plus z squared, plus this distance squared, y squared. In general, okay, if we want to figure out what the components are here, all I'm going to do for 3 dimensions is add on the square of the z component. Okay? I know this picture gets a little crazy. That's why multivariate is a hard class. The math in multivariable is actually pretty easy. It's the visualization and the 3-dimensional graphing that's kind of a pain in the butt. All right. So now, if I want to figure out the magnitude of A, I just take each of these squared and square root of it. It's just a 3-dimensional Pythagorean theorem. So let's go ahead and do that. So now, A squared will equal 4 squared plus 6 squared plus a negative 1 squared. This will equal 16 plus 36, which is 52, plus 1, which is 53. So A is equal to the square root of 53. B squared will equal, and I'll just go ahead and put the square root around it now, 5 squared, nothing here, plus, that's negative 5 squared, doesn't matter, 10 squared. So now, B will equal, you can take the square, oh, I should take the square out there, so put the square root sign. So now this is 25 plus 100 will equal the square root of 125. So now, doing this, I can say that A dot B is equal to A, B cosine theta. I know what A dot B is. A dot B is negative 30. A is square root of 53. B is square root of 125 times cosine theta. So theta is equal to the inverse cosine of negative 30 over the square root of 53 times 125. Plug that into a calculator. I get 68 degrees. Excuse me, 111 degrees, 112 degrees. forgot to put the negative in there. It's going to give you that, I should have just seen that as a supplement anyway. But, so that's how you can find the angle between two vectors when it's given to you in IJK notation. Okay? All right, we're going to talk about cross product next and then go over some problems.